Okay, welcome back, everybody. I hope you had a good lunch. I had leftover hamburgers, for those of you who are interested. They're pretty dry. Jamie, are you ready with your slides?
I sure am.
Okay, so let me just quickly introduce Jamie. This is Jamey Szalay from Princeton. He will talk to us about the Interstellar Dust Analyzer. Take it away, Jamie.
Great, thanks, Pontus. So yes, today I'm going to talk about the dust detection suite that we've been putting together a plan for. I'd like to thank all the many people that contributed. This was very much a team effort. I just happened to be the one presenting, but this was put together by a lot of meetings, and I'd like to specifically thank Casey Liss for leading the whole dust science and instrument portion of Interstellar Probe. So next slide, please. So I'm going to give a very short science overview, and the rest of the talk will be focused on the instrumentation. But I just wanted to highlight and remind everyone why dust is so special and interesting and important. So it's a quote from Eberhard Grün and colleagues, 2005. Dust particles, like photons, they're born at remote sites in space and time. From the knowledge of their birthplace and their bulk properties, we can learn about the remote environment from which they came from. So dust particles have an incredible amount of information that carry a mass, a velocity vector, a composition, a charge, and all of this tells us about both the environment in which it transited and the environment in which you're in yourself at the spacecraft. So next slide, please. The current dust environment in our solar system and our local interstellar cloud might very well carry imprints and signatures from the formation of our solar system. So billions of years ago, we had the sun in the nebula form, and over a lot of physical processes, it's been processed into the solar system and the dust environment that we know today. And so there are some really big open questions on how we can use both potentially interstellar dust and dust in our own solar system to characterize and understand both the environment in which our solar system was formed and then our place within the galaxy. And so both of these are interesting and compelling science topics that we can address with an interstellar dust analyzer. So next slide, please. With respect to interstellar dust, so our solar system is moving relative to the local interstellar material at some speed. And this is a nice graphic made by ESA and NASA that shows detections by the Cassini dust analyzer at Saturn, where they did measure 36, over a very long time, they measured 36 different interstellar dust observations. And so the interstellar dust is able to actually penetrate our solar system, and it interacts with our both sunlight and the solar magnetic field in interesting ways, and it's filtered in very complex ways. But we are able to actually have made constraints on the local interstellar flow to the solar system in our own solar system. So next slide, please. So this, in the bottom, there's a stack of 3 panels, and I'm sorry, it looks like it got maybe a little modified in a PDF conversion. But the middle panel shows a figure from Vera Sterkin and colleagues, and it shows that the flux of interstellar material is actually, depending in a size-dependent way, it's actually prevented from accessing the nearest portions to the sun, and this is due to solar radiation pressure. And so there is a filtration mechanism, and there's actually electromagnetic filtration that occurs for smaller grains. On the left shows various in situ dust detections by dedicated dust instruments, and it shows potentially this filtration where you have less fluxes close to the sun and higher fluxes far. On the right shows the solid line and the curve show remote-based measurements of what we think the abundances are of interstellar dust. And then the square boxes in blue show in situ measurements, and these are both as a function of mass. And what we found is there's a pretty big discrepancy on if we were to account for all the mass in the solar system or in the interstellar material and dust based on remote measurements, we get a very different picture compared to in situ. You can see that blue wedge shows the discrepancy where there's a lot more predicted small grains remote based, and there's a lot more large grains in the in situ measurements. So these dust measurements that we could make could determine the role of solid matter in the dynamics and evolution of the interstellar medium and try to resolve this discrepancy. And we could also make compositional measurements and determine if the local interstellar dust is consistent with the feedstock and the formation of our solar system. Next slide, please. In terms of interplanetary dust, while we're transiting out of the solar system, we can make very interesting measurements as well. So our own solar system, the dust out, 99% of the dust in our solar system is generated outside in the Kuiper belt. And there are way too many of these objects that we could individually fly by, but all of their material is being kicked up and incorporated into the interplanetary dust cloud, which then we could in a way we could measure remotely and get a statistical compositional understanding of the Kuiper belt with in situ dust detections. Additionally, we can provide ground truth in an astrophysical context, because when we look at other solar systems, what we see is emission from dust. And so by understanding, shown here on the left is the one specific solar system, on the right is a simulation of ours by Andrew Poppy. And so we can use our own solar system as ground truth and a sandbox to understand how these work and put them into astrophysical context. And please see a poster by Sean Shu for more interesting information about this. Next slide, please. So brief scientific overview is just to explain that dust measurements from Interstellar Probe can answer a lot of really interesting questions, both on the nature of the interstellar material and the formation of our own solar system. Next slide, please. So now focusing back on that, that figure that showed the discrepancy between remote and in situ, what we propose is a suite of 3 potential dust measurements, 2 of them by dedicated dust instruments. You can see on the bottom, as a function of mass, it shows the ranges of the various instruments we propose could make considerable contributions to the dust environment. And so today I'll be focusing on the dust analyzer and the dust counter. And I'll leave the NMS for anything that Andrew Gali might be talking about later. But what you can see is that the dust analyzer, which is the core science measurement that gives you composition, that provides a really nice range where we have the biggest discrepancy in small grains between these 2 observations. Next slide, please. So there's a variety of ways that you can measure dust in situ. This is an overview that shows many of them, not all of which we would employ. But the 2 that we would focus on are when you have a dust impact into a surface, it makes impact plasma, and it also carves out a bit of that material from whatever target it impacted. And so the physics of that impact process can be harnessed to then understand the properties of the impactor itself. So for example, for a very simple instrument like the one shown on the right, you can have a polarized material that when you carve out a piece of that polarized material, it generates a capacitive discharge that you can then measure out as a signal. It's a function of mass and speed, kind of momentum, and you can get some coarse information on the impactor flux from that. So next slide, please. If you could go to the next one. Thank you. So we have the farthest reaching dust detector ever flown is of this type. It's a PVDF detector, a plastic detector, and it's flying on new horizons. It's out to 50 AU and beyond, and it's been able to measure the flux of both interplanetary and potentially interstellar dust grains in our solar system. And so there's a high amount of heritage. You can see here on the left, this is about the size of a pizza box, and it's on the kind of the back end of New Horizons on the windshield, if you will. So next slide, please. And these are as of this week, even the best measurements we have to date. You can see it goes out to 50 AU. This is very exciting. Out past 18 astronomical units is the farthest reaching dust detector ever made before this instrument. So we've been able to really add a lot to our understanding of the Kuiper belt and beyond. You can see also the 2 curves show 2 model expectations. Right now, it looks to be more favoring in these 2 comparisons, Andrew Poppy's model that predicts that a lot of the dust is produced in the Kuiper belt and kind of sustains this broad density distribution. But one of the things that we don't fully understand is what is the total relative contribution of interstellar grains to this, because this instrument, it's a counter. It gives you the count rate as a function of impact amplitude. And so that amplitude is a function of the momentum in some way of the grains. And so to get out the mass of the impactors, you have to make assumptions on the speed or vice versa. And the flux numbers that we get here on the order of 10 to the -4 per meter squared per sec, those are comparable to the fluxes that we've measured of interstellar grains in the inner solar system. And so it could be that there's a big part of filtration that's going on. We don't fully understand what the relative sources are because, again, this is just a more simple instrument that it's difficult to tease apart these two sources, the interplanetary and the interstellar. So next slide, please. So to really get a kind of an order of magnitude leap in our understanding of the outer solar system dust environment and the interstellar dust environment, the most scientifically fruitful instrument would be a dust analyzer that has composition capability. So the way that this instrument works is you have an incoming dust particle, it hits this target, you can see there's this flat plate on the back. It produces an impact puff of ions and electrons. The electrons get collected on that target. The ions are then move away from the target because there's a potential, and there's this parabolic grid that focuses them into your ion detector, and that ion detector can be done a few different ways, but essentially what you want to do is measure the various amounts of ions and relative timings of their arrival. So next slide, please. The way that we can get mass out of that is because, again, so there's an electron signal on the target, there's an ion signal that carries the compositional information, and you can see here, and again, I apologize for the blurring, I think some PDF conversion happened, but you get a signal for the electrons, a signal for the ions, and then within the ions, you actually get a mass dependent timing. And so the higher mass ions take longer to arrive. And so you can bookkeep and you can figure out what's the compositional diversity within that specific impact. And you can get an idea of what the actual composition is out. So next slide, please. And it turns out that just due to the nature of impact ionization, the impact speed is really important in terms of what kind of information you can learn. And so this is a table put together by Zoltan Sternovsky that shows as a function of speed the various types of impact plasmas that you measure. And so, for example, at very low speeds, you actually you don't have the energy to pull apart, say, molecular bonds. And so you're not able to get, say, an individual bookkeeping of what the elements are. But it turns out at about 15-ish kilometers per sec, you're able to break the molecular bonds, and you get impact plasma that are formed just of the individual ions and the individual atoms from whatever was in that dust grain. And so you can do a really nice accounting of what are in these dust particles at the speeds that we're expecting for interstellar probe, which are on the order of many tens of kilometers per sec. And so this is a really promising way to be able to extract the compositional information for interstellar dust material. Next slide, please. So as I mentioned briefly, we have 36 measurements, compositional measurements from a similar instrument to date. So Cassini at Saturn had a compositional dust detector, dust analyzer. And up on the top is an example of one of these time of flight mass spectrometer measurements. This is by a paper by Nico Altobelli and colleagues. And you can see as a function of mass, we're able to separate kind of broad compositional groups. But again, just due to the improvements that we've been able to make in dust analyzer capabilities now, and especially with data rates and instrumentational updates, we can get a much finer time of flight resolution, which then allows us to do much finer spectroscopic analysis. And again, one of the big discrepancies, in addition to the mass differences as a function of size from that figure I showed, was so the Stardust mission also had 7 interstellar dust grains that were returned to the ground and analyzed. And the composition of all those grains was actually very diverse, and it's kind of very different from the 36 that were measured by Cassini, which all looked roughly similar. And so that's another ongoing mystery that we hope we could resolve with significantly more statistics on total interstellar dust measurements. So next slide, please. The way that we calibrate these instruments is there's a dust accelerator at the University of Colorado, so we can accelerate material of a known size and composition, and we can shoot it at one of these instruments and get a very good calibration. And these are really important because depending on the impact speed and composition, sometimes it's not very straightforward to invert the time of flight mass spectrum to the actual original mass distribution of the dust grain. And so fortunately, even in flight, we can do different calibrations on the ground to better understand the measurements that we're making in space. Next slide, please. Here's an example, again, showing the power of the instrumentation that we hope to fly on the Interstellar Probe. This was given by Sasha Kempf at University of Colorado. And it shows that with an expected abundance ratio of, say, magnesium, we can actually get magnesium isotopic ratios in this specific setup. And so our ability to constrain composition and isotopic ratios is a really promising and exciting prospect for Interstellar Probe. So next slide. All right, so in terms of the total specifications, again, I was focusing on the dedicated dust instruments here, the analyzer and the counter. There is an overlapping mass range by about a decade between the two, so we could potentially cross-calibrate them. The compositional analyzer, again, in addition to giving the composition, you have kind of a better idea of the speed based on the profile in the time of flight mass spectra. And so we can use the two to kind of cross-calibrate them. The compositional analyzer is a lot smaller than the dust counter. It's about the size of a big bowl, where the dust counter is about the size of a pizza box. We can get a composition range with the analyzer in the range of 1 to 300. You wouldn't really want to do more because it's pretty heavy if we're going to individual atoms and ions. It would take about 10 watts for the analyzer, 1 for the counter, 12 kilograms for the analyzer, 2 for the counter. Both are at a TRL of 7. And last, I'd just like to mention that the trajectory and mission design are really critical for the measurements we could make. So I did 2 cases here with the help of Andrew Poppy with his Kuiper Belt dust model, showing what it would look like if we went out to the nose. And the nose, again, would get us out to the quickest to the pristine interstellar material. And then I took the nominal case that currently exists for Interstellar Probe. It's 80 degrees out to the right, to the starboard flank. And it actually goes significantly southward. And because of that, we need to be pointed into the relative impact direction for interstellar dust grains. And so if we're going out to the nose, we're running right into the beam. But if we go out 80 degrees, we actually have to cant our instrument by about 34 degrees. And now it's on a spinning spacecraft. So it's only looking into that core flux. It's something like it reduces it to about 20% of what if you were just staring into it due to the instrument geometry. So in terms of interstellar measurements with composition, we'd get about 300 a year going out the nose, but only in the order of a few tens, 40 to 50 a year if we go out in this current trajectory. And so the statistics are definitely decreased as opposed to going out the nose. In terms of Kuiper Belt dust also, we would have a reduced total count rate, again, because we need to cant our instrument, so we wouldn't be facing the core flux from Kuiper Belt grains, and we also go way far south of the ecliptic plane, and so we lose the core density. So in terms of composition analysis, instead of 12,000-ish grains from various different Kuiper Belt objects, we might only get about 1,000, so an order of magnitude decrease from this. All right, so if you could go to the final slide. So in summary, I would just again mention that the dust instruments on board Interstellar Probe can answer really interesting questions, and they're cross-cutting between heliophysics, planetary and space science, and astrophysics. So thank you, and I'll be happy to take questions probably at the discussion.
Thank you, Jamey. Thank you for a wonderful and intriguing presentation here. You know, it's a very compelling topic to me. And also for the very useful